Today we'll look at some numbers. On the screen you see 5 numbers that are extremely significant in mathematics. Obviously 0 is the most fundamental number, and 1, and followed by the imaginary number square root of -1, and pi, the ratio of the perimeter to the diameter of a circle, and e, called Euler's number. Now we will focus on e today, and in this set obviously pi and e are the rational numbers and I is a complex number, and 0 and 1 are straight plain numbers, and all of these are related with an identity that is e to the power of I pi plus 1 is equal to 0. And this is a very well-known identity. Some people call it the most beautiful in mathematics. So we'll focus on e today and try to understand what e is. And e is defined as this formula in some situations. It's basically the summation of 1 by 0 factorial plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial and so forth till infinity. That is defined to be the value of e. Now where does something that strange come from? And that's because Jacob Bernoulli observed that if someone had given out a loan for $1 or 1 unit of money in those days, and he charged 100% interest rate per year, if the interest was only paid once in a year, at the end of that year you will get $2 back. However, if you ask the creditor to pay twice in the year, that they have to pay the interest during half the year and then at the end of the year, it so happens that the amount that you will get at the end of the year is not $2 as it was in the last case, but $2.25. And if you collected interest once every quarter, you will end up with something like 2.414, and if you did it once every 12 months, you will have something like 2.61. So you can see that the amount that you will get at the end of the year will increase based on how many times you charge interest during that period. And if you take this to infinity, that means you basically take interest and recalculate the interest every millisecond or so, you will tend towards the value of e. That's where the number comes from. So the rate of change and the study of that basically. Now let's try to calculate the value of e using some simple, let's try to do a small function ef, which will show us this trend. So we have 1 plus 1 by n to the power of n. And in this function, we basically are, here we have a small function ef, which is basically 1 plus 1 by n to the power of n, which is the formula for compound interest. And we can do this calculation for a series of numbers from 1 to, let's say, a billion or something like that, a huge number, in a geometric series. So the geometric series basically looks like this. Right? It's basically a ever increasing series up to a billion right now, and we can run this function ef on those to see how the value of e increases with the number of n that you're considering. So you can see that once it reaches about a billion, it basically reaches 2.8718, 2812, so forth, which is very close to the value of e. Now here we used normal type of numbers. So if you did go to, let's say, so if you used even larger numbers, at some point you will see that the numbers stop increasing and they go back to 1. That's because we overflowed the limit of numbers that we can deal with in the system. So we have a different way of doing the same calculations, and that is that will demonstrate even further some of the new capabilities of ZCubes, and that is that we can now take the same function, but we can give it decimal accuracy up to 500 digits, and we are writing the same function 1 plus 1 by n to the power of n, and they all have been designated as decimals of 500 decimal places. Now we are giving e function such a large input value and saying, let's say give it to 500 decimal places, and you can see that it now calculates e to a much higher degree of precision. And this is a very good way of doing these calculations, not just e but other things too, using ZCubes at extremely high amount of accuracy. And we will consider the e value in a slightly different way, more back to the fundamentals. So we have generated the value of e as a sum of factorials. So here you have sum of the inverse of the factorials from 0 factorial up to 100, and you can see if we added them up together, you get pretty much close to e, which is the original definition of e, which was saying that e was basically the summation of 1 by n factorial from 0 to infinity. So as you can see, if you go in a series like this, you will get closer and closer to the e value. Now you may be interested in knowing how we could create this series of numbers, and there is a function in ZCubes called series string. So, and we could provide a string that we would like to expand and give a series 1 to 100, and you can see that it gives you the series here. And I can now join these using the plus sign, and then you have a string. Let's say just for safety purposes, we can put these into parentheses. And here you have the expression that you want to evaluate. So you can simply copy this and then put it into another code module, and you can calculate this. Now I made a mistake in that I started with 1 here. I should have started with 0. So if I start this with 0 here, 0 dot dot 100, you will have this will add up to 2.718, 281, 828, and so forth. So which is very close to the value of e. Now this again demonstrates the ability of ZCubes to handle with variety of series and infinite series and decimal place with high amount of precision and so forth. So thanks for watching. So that's what E is about, and hope you enjoyed it.